那你可能会先介绍。First, the jury please introduce themselves. First, I am 张明哲 from 师范大学。
蔡尚放，台湾大学物理系。
张慧珍 from 彰化师范大学。
陈国国中正University。
Thank you. And reporter, please introduce yourself.
Okay, so hello everyone. My name is Daniel, and I'm here representing my team, which is 明道美 M. We're from Taichung 明道高中. Yeah, thank you.
And opponent, please.
I'm Akshar Jr. of Nomnayas. My team consists of Thomas, Richard, Cedric, and Gary.
I'm from Taipei Regional High School, and I'm the captain of Palace, and this is Water, this is Wish, this is Ken, this is She's Week. Thank you.
Okay, let's start okay, the opponent please propose one problem.
No-niters challenges number 11, balls on an elastic band.
Number 11.
We'd like to reject the challenge.
With challenge number 7, 3-sided die.
Number 7.
We'd like to accept the challenge.
Thank you. And we have number 7, 2-sided dice.
Good afternoon, our competitors and judges. I'm Yang Chen from Mingdao Mayhem, and today our topic is number 7, three-sided dice. And this is our outline. At first, we'll have our problem statement in experiment medium, and we'll go to our terms definition. And then we'll talk about our experiment method like setup and other things. And for experiment 1, we're going to find the dice's height and radius. For experiment 2, we're going to see if the simulation fit our static geometrical theory. For experiment 3, we're going to see the real experiment result. And we'll have our conclusion. And this is our problem statement. To let the coin on its side is often associated with the idea of a rare occurrence. What should be the physical and geometrical characteristics of a cylindrical dice so that it has the same probability to land on its side and one of its faces? And we will mainly focus on the same probability dice. And this is our experiment video. As you can see, there's a funnel on there. So when we throw a dice into the funnel, and it will drop, and after a period of time it will stop. So we can record the result to see if it is from side, back side, or standing side. And we're going to define what is solid angle. A solid angle is like if we have a surface on a sphere and we want to know how big is the surface to the whole surface area. So we can get the integral. We can use integral to get the area we want to know. And so we define the solid angle omega as the A divided by R squared. And this is solid probability. It's like when we use projection from a centroid to an object's side, and how big is the probability when we randomly choose a point on the sphere and the corresponding side it is. So the probability we mean is the area solid angle divided by the whole sphere solid angle. And present underside probability PS can be get from the solid angle probability. We first get the omega B1 CB2 as the triangle of one of the triangle on the underside. So and it will be like a formula. And also we want to simplify the equation, so we define R as 1. So the PS will be n times omega B1 CB2 divided by 4 times pi, which n is the side of the underside polygon. And we want to calculate the cylinder's probability from prism's probability. And how it works is when you n the size of the underside that polygon, when it goes to infinity, so that is a cylinder. And we can, according to the Taylor extension and other mathematical calculations, we can get the final value of the probability. And this is our experiment setup. We have a metal frame and to hold the funnel, and we throw a 3D printing three-sided dice into the funnel, and the funnel is used to let the dice have the initially random angle. So we can record the result like this. And we throw the dice one by one and record the result. And repeat the 1 and 2 steps until throwing 1,000 times. And the relevant parameters we use is different height and radius ratio. And the experiment 2, we use a different math, and we get the result by computer physics simulation. And for a different math, we get the result by using real experiment. And for experiment 1, we change the height radius ratio, and we define load as R divided by R, H divided by R. And we want to get the best load to be a three-sided dice, so the standing probability should be a crater. And as you can see the image below, we change the load and so as to change the height of the cylinder. And the manipulation variables is the height of the dice, and we have a corresponding ratio load. And the radius is 1, mass is 1.02 grams, and the material we use is PLA, and the initial throwing height is 25 centimeters. And this is our experiment data. As we can see, when the height of the cylinders keeps growing, and the standing probability will keep growing. And as you can see, the trend is become increased slower. That's because the result can be more than one, so it must become slower like this. And we compare our experiment results with the theory data, and we know that the undersized person cylinder's probability is PC. So the size probability is 1 minus 2 times PC in according to the symmetry. So as you can see the right side of this diagram, we can see the experiment fit the theory data. Also, so we can draw a line to the 0.33 this probability. Also, we can get the height of the three-sided dice height. So that we can get the dice's height is 0.7. For experiment 2, we have the best ratio we get from the first experiment, and we're going to verify the geometrical theory by changing mass. And now we have to use a simulation. And we have a program, we multiply the mass, the cylinder's height, and the bounciness to simulate. And let's say the simulate video. As you can see, it will bounce a pair of times, and finally, when it stops, the program will calculate the result automatically. And we get the cylinder's height that is 0.7. So we can use this cylinder for our dice to do the experiment. And the things we change is the 3D printing fill rate, and we will have a corresponding mass. And the radius used is 1 centimeter, and the load is 0.7, and the material is PLA. Initial height is 25 centimeters. And this is our simulated data. And as you can see, when the mass of the dice increase, the probability does not affect. So the simulation fits the geometrical theory. The mass does not affect the probability. For purpose experiment 3, according to the first experiment, we're going to verify the geometrical theory by changing mass. But now we're going to using a real experiment to see what happens. And this is our data in a real experiment. So in a real experiment, we know that we can find that it does not fit the geometrical theory. So we need to use some physical theory to expand this chain. And this is a model we use. A N of t is the normal vector of the cylinder, and alpha t is the angle between the N of t and the z-axis. So every stationary state has its gravitational potential energy. As you can see, when dice is standing, and we define that its energy is EE. So like when the EH denotes that the energy when the dice is front side or back side. And as you can see, we denote EL as the R squared plus H divided by 2 square root, and EE denotes for R, and EH denotes for H divided by 2. So now we can expand this peak. Why will it have this change? So the En is the energy after it bounced n times. So we know that only in the EE to EL interval it will be standing. That is the energy of the cylinder should be bigger than EE, so that it has enough potential energy to stand. So we can compare the dice standing probability to its collision energy constant. Collision energy constant is like the initial energy is E. So when it bounce a times, the energy after that is gamma times EU. So when the gamma is higher, the energy will keep decreasing slower. So it's more likely to be in an EL to EE energy interval. And for experiment and simulate comparison, we can find that what causes the result. The two data is different is because in the simulation, the ground we use as a rigid body, so the dice spins very quickly. So the energy, the initial potential energy is used to spin a lot. So the energy also lost a lot, and the And the energy loss constant we talked previously does not affect much to the probability. Okay, and that's our conclusion. If a ground is a rigid body, the geometrical characteristics should be height divided by arc radius as 0.7. However, there is no 100% rigid body in reality, so we should consider a physics characteristic, the mass, the gamma to explain the phenomenon. And if the gamma is higher, that means the probability will be higher. And if the mass is bigger, the probability will be higher. Thanks for this.
Okay, thank you, reporter, for a wonderful presentation. So I would like to ask you some questions before we begin our discussion. So first, did you consider escaping probabilities?
Escape? Oh no.
Did you consider the x? So when you have a coefficient of restitution going down, bouncing up, do you consider the x motion of the cylinder? Because that would decrease the amount of restitution.
In this experiment, we don't consider that.
Did you consider well energies?
What?
Well energies.
No.
Well potential energies. Okay, and it seems like in your equation, the probability only depends on its height.
Height?
Yeah, the height of the cylinder.
No, the probability is affected by the coefficient.
Please go back to that.
Where?
It's okay, let's move on. So did you consider that the dropping of the dice is a chaotic system?
In this experiment, we doesn't consider.
You don't consider this is a chaotic system?
No.
No, okay. Do you have any error bars or any error analysis at all?
No, and this is
This is a yes or no question.
No.
No, okay. So you didn't graph your theoretical equations at all?
Yeah, here's a sort of theoretical. Here, this is a theoretical data.
Okay, I was expecting the curve. So you don't have error bars. Did you consider the use of steradians to model the possible landing edges?
What?
Did you consider the use of steradians to model the landing characteristics?
No.
And finally, did you make your computer model?
Yeah.
You made your computer model based on the fact that it's not chaotic? Because you said earlier that it's not chaotic.
You can talk about it.
Okay, today I will be opposing three-sided die. My name is Alex Jr. from Hayes. So here's a poem statement. You can read it by yourself. First, we'll identify our ideal structure of investigation, which will start with the type of motion of the coin. We'll define the real relevant parameters. We'll test and model probabilities, and we'll find ideal characteristics. So here are the pros and cons of the report that was given by the reporter. First, there was a relatively clear demonstration. We could see what was going on. He showed the experimental side setup. He had some modeling for his dice, and he also demonstrated repeatability in his experiment. The cons for this experiment, however, there was no qualitative explanation for the phenomenon. You do not define the coefficient of restitution rigorously, nor is the coefficient of restitution used correctly in this phenomenon. Unfortunately, you did not incorporate friction, which accounts for x-axis motion and also affects the coefficient of restitution in your argument. You did not account for the chaotic system, which basically invalidates many of the arguments. There's no comparison, I meant to say there's no error analysis between your comparison of theory to experiment. You didn't mention escape probabilities or even well energies. That's wrong. There's no best fit line for the theory with error bars, and there are no error analysis, nor were there any citations. So, points of our discussion. First, we'll talk about your experimental parameters and how they didn't account for a really important part of the experiment, which is chaos. The second, then we'll talk about what truly constitutes this chaos, what contributes to this chaos, and the implications of that. Then we'll talk about well energies and stir radians and escape probabilities, and we'll attempt to construct a more rigorous theoretical model using this. Then we'll move on to his experiments with error analysis, computer modeling, which also has effects on chaos. His standing probability, which was really odd, I had to make sure of something. And we can start our discussion, please. Okay, so upon Mr. Reporter, could you please, So please turn to your the phenomenon demonstration slide. So approximately what height did you drop this from?
25 centimeters. We control that.
So you said you wanted to drop it from a random height?
Random angle. And the funnel is used to have a cathodic signal.
Can you consider that just by raising the height you can make the system more random?
Raising the height? Oh, no. We consider the random angle as the main point that we should control. Sorry? The angle is random so that we can control, that is our control variables.
Right, so my problem with this this theory of logic is that the angle you drop it from, or the velocity you drop it from, or for that matter, after achieving a certain height, the height you drop it from is completely irrelevant to the experiment because the motion of the coin is chaotic. Do you know what chaotic motion would be?
Yeah.
So you know dropping a coin will be chaotic, right?
Yeah.
So this project is about a coin, and the coin is chaotic, and you didn't take into account chaos. And yet you're talking about random, like angles being random.
Yeah.
But you didn't think that just by, even if you hold it at heads relatively still, even after it drops to the ground, after a few rounds, it's still going to be random.
Yeah, but we throw like this into a funnel, and that is a chaotic system.
Yeah, but you don't need to do that for it. It's always chaotic. There is nothing wrong with doing it this way. It just demonstrates a lack of knowledge of the experiment. So that was what I wanted to cover with the chaotic system. Now could you please move to your theory slide? Yeah. Actually, it's slide number 7. Oh wait. Yeah. So this said the probability of landing on sides, I presume.
Yeah. No. That is unprecise probability.
The probability of landing it on the downside.
One of the
So it depends on h.
Yeah.
But not on. Oh, you already assumed the radius is 1.
Yeah, we assume the radius is 1.
So how do you account for did you account for all the possible ways integrating over a surface that the cylinder could land on?
Integrate?
No, not just an integral. You can't demonstrate with just an integral. So, for example, did you take into account, sum up all of the possible, with the surface and integral, all of the possible sides the cylinder could land on? Or did you find a way to show how you could possibly do that?
Possibly to rephrase again.
Okay. So you're dropping a cylinder.
Yeah.
And since you already established that the motion is chaotic, it can basically drop on basically any point with or tangent line.
Yeah.
Did you take into account every single tangent line in your, if you have a surface integral? I don't think you do.
For solid probability, there's a random random contact point on the sphere, so we can get a solid probability to end on one of its side. So we can know the probability by know what side of the object that is corresponding to.
Okay, so I think I understand you now. So basically you're going to have a tangent line to the sphere, and then you're going to shrink it into the cylinder, and then you're going to see what contact point you touch it.
Can you define what is the tangent line?
Oh, you don't know what the tangent line is?
I don't even know.
No, that is a secant line. It's okay. It's alright. This recorder. If you need help defining tangent line, I can help with that. Actually, let's just do that first. So if you have x squared plus y squared, you have a circle over here. This will be a tangent line.
Okay. And
your teammate was. This is the secant. No. Anyways, I was mentioning earlier, you have a sphere over here.
Yeah.
And you can have a tangent line to that sphere, right?
Yeah.
You can have infinite possible tangent lines of the sphere with stereoidians 2, 4 pi. We took that into account.
The solid probability we know we use as like there's a tangent line has a tangent line and a sphere has a contact point.
Yeah.
Yeah. So the solid probability means when this contact point is corresponding to which side of the object is. Like if a contact point is here, so the side is here. The corresponding side is here. Like if a contact point is here, so we know that it is corresponding to the standing side here.
I would like to offer a bit of clarification. So when I think I think this way of defining is incorrect. Basically, what you do is you have a tangent line to the sphere, and you move it in until you find the tangent line. What you did before to the cylinder, and that's a bounce point. What you did before was you put a point and you arbitrarily said, okay, it moves down over here. You arbitrarily wrote, it moves down over here.
So we use solely angle to define how big is, and like we use projection. So projection is like this, and so
yeah, you do project it.
Yeah,
in words, but not arbitrarily. Okay, let's continue with something else. So could you move? You were talking about something about probabilities of escaping or of landing on edge. Could you move to that side, please? Maybe a little. Okay, these are experts. Okay, never mind. So I remember you had a diagram earlier that had 3 dice and said one was like this, one was around like this. Do you remember?
Okay.
And one was like this, right? So these actually they could represent the edge-induced probabilities. So an interesting way to think about the problem, which you can try to include in your presentation, I think would make it a little more rigorous, is if you have a certain cylinder oriented this way. The edge-induced probability will be the probability it lands on its edge. Well, just to be clear, by edge I mean this side. And the head-induced probability will be the probability it lands on one of its heads. So in this case, it will be right in between the edge and head-induced probabilities. Whereas over here, this would be an edge-inducing probability.
And this is just our solid angle probability. Just that's another way to express this.
Right, but that we haven't gotten to my point yet. Basically, after you bounce it, it's going to bounce back again, right?
Yeah.
So, what it needs but as we were talking about potential energy. Yes. So it needs a certain energy to bounce back again. the important thing about the energy is that it needs to jump back to this state, where if it is edge-inducing probability, it can go to a head-inducing position. And if it is currently at a head-inducing position, it has enough potential energy to go back to an edge-inducing position, and vice versa.
Yes. So we have this critical energy and this critical energy. So when the energy is between this is called EL, and we call this EE. So energy is in the interval of these two energies. So it has enough potential energy to let it stand.
Right, it has enough, but that doesn't mean it will stand, because even if it lands on the ground multiple times, it can always land like this and go bounce, 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 bounce.
Yeah.
And even though originally it has.
So I say, in this interval, it can be standing, but not 100%.
Okay.
So we can use the interval to describe how this happens. So if the collision energy constant is bigger, so it is more probable to in this interval. You know why? That's because we have initial energy, and the gamma collision energy constant is higher, so it can decrease more slowly to fall into the energy interval.
It can decrease more slow. I don't think that's a very rigorous way of defining this. That's okay. We'll move on to your error. So it's very kind to have. Are these your experiments?
And this is an experiment.
So I noticed that for experiments, you only change the ratio of height to radius and mass. May I ask why you would even think of changing the mass? Because if you have a coin, if you have a 50 NT coin, that's much heavier than a 1 NT coin. So obviously the chance of landing on heads and tails are the same. So how is mass even relevant to your experiment?
Okay. There's 2 points, and the first point is that in our experiment, the mass will also affect the collision energy constant, and so you can see in these two diagrams, so it will have the same thing. And the other thing is that so as you can see, this 1.02 grams and this 2.5 grams. As collision energy constant is really close, but the probability isn't the same. So we can know that.
Okay. First, you can't say probability isn't the same because you don't have error bars. How do I know if this error bars is like tiny or if it's really large? You can't say that, but it's okay. Let's move on.
How do you define what is the error bar?
Do you not know what error bars are?
No. What I mean is that when you.
It's okay. Let's move on. So I want to talk about. We agreed earlier that the dropping of a coin is obviously a chaotic system. But how do you model a computer based on the chaotic system? I don't understand, because that's not how computers work. Did you find this online?
We use a program, not online.
You wrote a program that describes a chaotic system. I must say, that's very talented of you. But I won't get into the specifics. And finally, do you have any?
We run a program that initially it is a chaotic system.
Yeah, so it is a chaotic. So you knew it was chaotic, but you still wrote a program on a chaotic system. Okay, so finally, do you have any citations?
No.
No. Okay.
No. My
answer
is
my
that.
question.
Okay, that was up.
Can you tell me?
So the reporter and I had a discussion that included his experimental apparatus, his misconceptions about the theory, his experiments that demonstrated such a misconception, and we came to a consensus on some topics and not on others. So topic 1, he didn't consider that raising the height would change the results. He didn't talk about the chaotic effect of dropping the die, even though he admitted earlier that such a chaotic effect would exist and change his theory. He didn't take into account the possible position that the cylinder can lay on using steradians and the sphere covering the dice. We talked about edge-induced probabilities and that potential energy needed to bounce back. On that point, we came to a consensus, but changing the ratio of height to the mass, I still don't understand why we would even think about mass as a relevant parameter and it affecting the collision energy constant and the chaos of the system. Thank you.
So we're ready? Okay. So the first question is for both of you. How can you ensure that in your experiment that dice leaves at a random angle?
We use a funnel. We use a funnel and throw it in the funnel, so it will have a random angle.
But it has an angle here, and how do you ensure that when it falls out of the funnel, it's at a random angle?
No,
like the radius of the tunnel might also affect the motion of the dice. So how do you ensure that it's random?
So why do you think the funnel is not a random? Well, it's not called a random angle.
It has a round side, and you have a precise angle here, and if it might have some rotation, and besides the radius of the hole right here can also affect the dice fall out of the tunnel. It might also affect it. How can you ensure that? And I think the opponent have also mentioned this problem, right?
Yeah, I mentioned this problem that the randomness of the angle does not affect, the starting angle does not affect everything because it's chaotic. I have a 10 and T coin, I'll drop it like this heads right now. It lands on heads. And even if I drop it again, it can still land on tails because this motion is obviously chaotic. It doesn't matter whether I drop it like this or like this or like this.
Okay, thank you. And how do you think the reporter can maybe improve their experiments?
Oh, that's a valid setup, but I just say it demonstrates a clear misunderstanding of the problem. So you can do it like that, just really misunderstood.
Okay, thank you. And for reporter, if your simulation is not a chaotic system, then how do you interpret your simulation data?
Interpret our simulation data. Well, that is a chaotic system because we change the environmental data, so it will have a chaotic system.
Okay, thank you. And the final question for both of you. If I drop the ball and dice with the same mass and with the same initial condition at the same height, which one do you think will fall faster?
What?
If I have a ball and also a dice, which I mean normal dice, the cube one, and you drop it from the same.
It depends on how thick it is. If you have a dice that's this big, it's going to drop faster. But otherwise, it's going to, if they're two of the same thing, they're going to drop at the same rate.
And how about
Can you repeat the report again?
if I have a ball and a dice with the same mass and same initial condition, and I drop it from the same height, which one do you think will fall faster?
If we cannot consider air force, it will fall down in the same time.
Actually, Argo thinks that it will be the ball because of when you drop a cube from a certain height, it will have precession. Do you know what precession means? Like it's in slow motion when it drops from the height, and we don't see any consideration of precession in the experiment.
I can demonstrate this one. Yeah, but you can't simulate a chaotic system. That's not possible. Unless you already know the process.
the reviewer, please.
Okay, here, honorable judges and with the competitors, I'm the reviewer of Team Palace, and we're going to review current number 7, 3 dice. And so this is our problem statement, and the focus should be physical, geometrical features, and the dynamical performance. So first, we would like to sum up what reporters have said in their reports. So the phenomenon is that 3-sided dice is an unchaotic system that probability of different landing scenarios are dependent on the ratio of x, according to what the reporter says. And their theory is that it's according to the solid angle and solid probabilities, and prisms on their side solid probability and cylinders probability. And the parameters they have is the ratio. So when the height of the dice is, they conclude that when the height of the dice is 0.707, the probability of landing on different scenarios is the same. And the mass of the dice will not affect the result. So here's the pros and cons of the reporter. The pros is they have clear theory and math calculation, and they have considerable data to support the theory, and they use program to simulate the experiment. However, they don't have real statistics, and they didn't put in error bars onto their charts, and they did not consider the system to be chaotic. And the funnel introduces too many variables to their experiments, and they fail to show the physical experiment process, and they only show the result. And here's the pros and cons of the opponent. So the pros is that they have on-point question regarding the chaotic nature of the system, and the con is inefficient discussion. So here's some summary of their discussion. So the first discussion they discussed about is whether this is a chaotic system or not. So the opponent's stand is that different height can lead to a chaotic result. However, the reporters did not think that this system is chaotic. And from our view, we think that opponents should take the chaotic nature of the system into consideration. Sorry, the reporters should take the chaotic nature of the system into consideration, which is impossible to be simulated. And the second discussion is about the tangent line. So the opponents say that they did not take all the tangent line into consideration, while the reporters, the projection of reporter is then is a projection of contact point. And for us, then we agree with the opponent because the reporter's statement is based on assumptions that cannot be considered. And the fourth discussion is about the computer simulation. So the opponent thinks that it is impossible to simulate a chaotic system, while the reporter they wrote an entire program by themselves. And so for our stand is that it is impossible to simulate. If the program did not reflect the reality of chaos, it is not necessary for the simulation. And here's some points we would like to point out. So first they have the false and concerning chaotic system, and they have faulty experimental setup, and they did not put precession force into consideration. And the mass is not valid physical characteristics, and so therefore the report did not answer the question fully. And this is our review. Thank you.
This is a concluding remark for the reporters. For discussion 1, opponent said, do you think that this is a cathodic system? Reporters said, yes, we believe that it is a cathodic system. However, opponent mentioned that whether using a funnel or not, the system would still be chaotic. However, we believe that by using a funnel in the experiment, it will assure that the angle would be more random since it is dropped at a lower height, that it is possible that no bounce support occurs. And opponent says that, did you consider the head and edge of it, including in a theorem? Reporters, and we say no, we did not consider the head and edge including inducing theorem. However, this theorem is only another perspective as same to the solid angle probability, which the opponent did not understand fully. And opponent says that, why do you change the mass? How is it relevant? And we say, since the collision energy constant is different in different masses, and the collision energy constant and also differs the moment of inertia, so such that the probability will differ. And then says, how can you write a program based on a cathodic system? And we created an approximation of cathodic system. Motion simulation through we use the environmental variable inputs to add randomness to the program. And for the conclusion, the opponent did not raise various interesting variables in theories. However, the theories are almost at the same and can work with the theory we provided. And there are many misunderstandings in the discussion, such that the point raised by the opponent is not very clear and sometimes misleading, which made the discussion very inefficient. Thanks.
Thank you very much.
I have a few questions. First, for the opponent, what do you mean by chaotic? Means randomness?
Sorry?
What do you mean by chaotic?
I think chaos is defined as small changes in initial conditions producing vast differences in experimental results. So for example, if I hold a coin like this, if I tilt it by 10 to a negative 10 degrees, it might produce a different result than if I just hold it at 0 degrees.
I would think, I prefer to call it randomness instead of chaotic.
Yeah, that.
I really don't know why you keep emphasizing chaotic, the word chaotic system. That's something probably I don't know, but my understanding is it's just randomness, it's not chaotic.
My apologies, but if I think chaotic.
No. My second question is for the reporter. Where in your experiment leads to you to conclude that the rigid body is important? I don't see any point, anywhere in your experiment.
Because rigid body.
Concept of rigid body.
Because in a rigid body, the dice will spin very quickly after every time it evolves. So there are a lot more energy to use for the spinning energy.
Rigid body means upon collision, the body itself won't deform. That's what we call the rigid body. Is that right?
Okay.
When you make a collision,
Yeah.
the object you consider does not change its contour. That's rigid body.
Yeah.
Then, where in your experiment tells you that rigid body is important, I don't see. It seems to me the concept of rigid body just jumps out.
And in the simulation, because the ground we use it as a rigid body, so every time it's bounce or collision, there's a lot of initial potential energy used to spin. So it will affect the probability that it will jump over the EL to B interval. This interval that the dice spin.
Okay. One more question?
Go ahead.
I have one question to the reviewer.
Yes.
That you mentioned recession force.
Yes.
And since the two teams didn't, why you think what is recession force? And why you think this is important?
Because this is not a round body, and when we're dropping this from a certain height, some of its gravitational energy, potential energy might be transferred into precession energy, and it will move somewhat like this. And here, therefore, it will have some effects on the system, and we believe that we should take precession motion into consideration of this experiment.
I think I will call it wobble instead of precession.
Is that a kind of force or?
It's
or
a kind
phenomena?
of it's a kind of energy, precession energy. Yes.
It's a kind of energy.
Yeah, the same kind of.
Is it a kind of rotational energy? Please.
Yes.
Yes.
So we think
You
that
don't have to call it precession, right?
What do you mean? I'm sorry.
You don't need to call it precession.
Oh, yeah.
It's just translational kinetic energy or center mass plus rotational energy about center mass. Excuse me. I want to get back to the report. In making simulation, you control the initial, you have an initial condition which is supposed to be randomly arranged, right? And you say by changing environmental parameters. What do you mean by that?
In the simulation in informatics, we can use the environmental variables to control the random.
What environmental parameters?
In the simulation, we can we use the time to randomize the angle of the
Time of dropping or what? Or time of falling? Time of what? Time is changing all the way.
Like environmental variables and we can use that to create a randomized variable.
Thank you.
Thank you very much.
Thank you.
Source of the reporter are 67676. And the scores for the opponent are 77656. And finally, the scores for the reviewer are 77756. Thank you. And then let's take the break.